Okay, good morning everybody. I hope everyone's having a wonderful day today. So just a couple of things I just want to mention. So first, the other day you should have received a message about a student experience survey for the course. I encourage you to complete this. I appreciate any feedback that you can provide. This kind of stuff I take very seriously. I do want to note that the information that you provide is anonymous, and it will only be given to me after the class. I always like to say it's almost like I'm getting a holiday card after the class for my students. So whether it be bad, good, please, that feedback is helpful for the department. And also, I like to look at it every time and see what I can do to sharpen up my craft. But if you like what I'm up to, just make sure you let them know. So, other than that, assignment 3 is out. Do keep in mind that the deadline for that's coming up next week. And also, I made a couple notes about that in a message I sent this morning, but nothing special or anything important. But one last thing, later this week, I'm going to start putting out exam preparation materials. So for example, I'll be putting out some sample problems. I'll be also putting out a mock quiz. That'll get you some idea of what each problem type will be like when you complete it over the final exam. And lastly, I'll give you the exam format. So I'm right now preparing all of these things, so I'll be getting them and releasing them to you as soon as I have them prepared. Okay, everybody? So hopefully, I'm hoping to get that to you as soon as I can. So, anyways, are we excited to talk more about binary search trees today? Give me 2 thumbs up. I know it's Monday, but I gotta get you into the mood to do this. No, wonderful. So let's get back to where we were last day. So last day I introduced you to our algorithm for smallest. So this algorithm would it gives me the node that contains the record with the smallest key. So remember, the idea here is because of the binary search tree property that our binary search trees have, I can move to the left in the tree, and every time I do this, every one of the keys that's in my left subtree is always going to be less than all of the keys, whether it be my node and all the ones in the right subtree. So if I keep going left, I'm always going to get smaller and smaller and smaller keys. So this is how this algorithm works, right? If I give you a leaf, this is the equivalent of an empty binary search tree, because when I give you an empty binary search tree in a representation, it's just a leaf node. So if this happens, you just return null. Otherwise, I have at least one internal node, implying there's at least one record. So all I do is I point at that, and then I just simply go as far left as possible. I find the leftmost internal node. So the way I do this is I keep going left while P is an internal node. When I exit this loop, will P be an internal node or a leaf node when I exit that loop? It's a leaf node, yes. So it's a leaf node, so I get the parent of it, so that, and remember, if I get the parent of it, then I'm going to get the record in question. So this is our algorithm here. We're going to go through the complexity analysis here. So let's figure out what the time complexity of performing the smallest operation is. So I thought I would do it a little differently than I usually do. Usually in the notes, you'll see that I usually use line numbers to be helpful. So I thought I would do at least one example of doing this in class. Normally I group them, but I can group them also this way as well. So let's talk about the time complexity of this. And you're going to find that the analysis for many of these algorithms is going to be like this. So I'm going to go through one a little bit more carefully first, and then I'll go a little faster. How's that sound, everybody? Because a lot of these are going to have a very similar structure. And we're going to see that there's a very interesting property our binary search trees actually have that sort of serve as a consequence of this. So the first thing I want you to notice is I have line 1, line 2, and line 5. They're all outside of this while loop. So I'm just going to count all of these operations. So I know lines 1, 2, and 5 all take some C1 operations. So that's some constant number of operations. And line 4 itself is just an assign. I can always get the left child in constant time because it's just an attribute of a node. So just like if I wanted to get the next node in a linked list, I can do that in constant number of operations. And line 4 takes some C2 operations. So, this one part I have not counted for is this loop here, right? So the question is, how many times is this going to perform a complete iteration at most? So I thought it would be helpful to kind of just doodle a picture off to the side of our analysis. Just remember, this isn't the analysis itself, it's just to help us think about this. Because remember, all I do is I always go left, right? So I start off with P up here at the root, and every time I go left, then I go left, then I go left, then I go left, right? Well, think of this. If I'm actually counting this up, well, I'd start off at the root itself. So I start off here, I do an evaluation of this. So right now I'm at the root, I check this, then I go left. I check this, then I go left. Then I check this, then I go left. And I keep doing this. Now, I would like to have a nice bound on this, and a very natural one might be, if you actually think about this, because remember, each time I check it, and then I go to the child, right? And I check it, I go to the child. So notice that this can never exceed the height of the tree plus 1. If I wanted to be extra generous, I'm just going to be extra generous here. So the number of iterations of the while loop. The while loop is at most, the number of nodes, it's the number of nodes in the leftmost branch. So I'm just going to count up how many are there here. Right? It can't exceed this. But what is that? Well, that is just the height plus 1. Which is no more than height plus 1. So it's no more than the height when you add 1 to it. So if I put everything together, the time complexity is the following, right? So the total number of operations, I'm just going to put all this together now. So I know lines 1, 2, and 5 all take a constant number of operations. They happen outside of this while loop. Well, that's just C1. And then I have C2 inside the while loop, and I want to take that with the number of iterations at most of the while loop. So I have C1 plus C2 times the height plus 1. But what is that in terms of big O? And keep in mind, I'm going to keep it simple for now. I could keep, yeah, it's big O of the height, exactly. It's just big O of the height. Now, I haven't got really much into the structure of the tree yet. Right now, we're just going to keep it with relation to the height for now. We'll talk more about how bad the height can get, because the binary search tree can have a lot of different structure to it, and I would like to have some way of expressing this more appropriately using the input size. But right now, we're just going to say it's big O of the height. We'll get into more detail about what it is in terms of n later this lecture. So all the steps of this make sense to everybody. So all I'm doing is I'm bounding the number of iterations in terms of the leftmost branch, which in this case is just no more than the height plus 1. In fact, this is true if I were to go from, say, the root to any one of the deepest nodes in this tree, which will be a leaf node. it will surely be no more than the height plus 1 regardless. So this is a useful property that we're going to use throughout this lecture. So that's what I mean by similarities. So I want you to take note of that. So just like pick it up, put it behind your ear and be like, okay, we'll need that later. So is this analysis clear, everybody? Any other questions before we move on to our next operation? Okay, so far we're doing okay. Give me 2 thumbs up if we're okay. Do we want to now see how we can discover stuff in a binary search tree? Okay, so we know that we can actually navigate through this almost it's just like the same idea that we had with the linked list, right? Where we can go each successive node, but now we have a left and a right as opposed to just a next. So as soon as you notice that, really a lot of the patterns here seem to make a little bit more sense, but we have an additional property we can use. We have the binary search tree property, right? So that's going to bring us to our get operation. And you're going to really see how, even though we used it minimally here in the smallest operation, how it's going to play a critical role in how we actually use the binary search tree. So you might say, oh, that smallest operation, that was kind of cute. You got left all the way. So how far can you take this idea from the binary search tree property? So what we're going to do, so I've drawn you the same tree I've had. Keep in mind, I'm going to draw this tree quite a bit. So just if you're wanting to have one master binary search tree you're going to play around with, it's going to be this one for today's lecture. So I may draw it a few times. It'll be kind of funny. So what I want to do is I want to motivate you to why we can use the binary search tree structure as opposed to just trying every one of the nodes. So for example, I could literally just do an in-order traversal of this entire tree and find the key I'm looking for, right? I could examine the entire tree. I could do this, in fact, just this idea as well with just a pre-order or post-order traversal or level order traversal. I could examine all of the nodes, right? And I could just see if it's there. But the thing is, the binary search tree isn't just any old tree. It has a lot of lovely properties we can use. We can use the binary search tree property to help us. So here's the idea that I was going to propose for you. So remember, the binary search tree property, just to remind you, if I look at any one of the internal nodes here, if there are keys in the children that they have, the left subtree, so the one that will be here and all of its descendants, or the right subtree, all of its descendants, the keys in the left subtree are always going to be less than my key. All the ones in the right subtree are greater than my key. So what we're going to do is we're going to navigate ourselves through the binary search tree, almost like I'm going to be directing myself from the root. So for example, remember, if ever we're looking for a key that is less than the key we're currently examining, do we go left or do we go right? Suppose it's less, go left. So what we're going to do is I want to imagine that I'm right here. Suppose Miss Kitty is sitting right here at the root of the tree. So what we're going to do is we're going to start at the root of the tree. And what we're going to do is we're going to direct Miss Kitty down to where we would like to go. So for example, we might hit a leaf node if it's not here. Or we might hit, for example, an internal node. In that case, we found it. We're going to direct it to go left if the key is less than our current key, or we're going to go right if it is greater than our current key. So let's do an example just to give it a flavor for this. Actually, let me use a different color here. So what we're going to do is we're going to try doing a get operation. Let's go get. Let's try doing get, or imagine I'm looking for a specific key. So in this case, imagine I'm looking for, let's go for 11. So right now I'm at 10. So if I want to get 11, well, which way should I go? Left or right? So 10 is less than 11, right? So we're going to go right, exactly. So we're going to go right. So, sorry, that's left. I mean, right. Thank you. Thank you. We're going to go right. Let's go right. We did this because 10 is less than 11, right? Now next, so you can imagine this just like the same exercise we went through over here, except now we have to compare the keys against ours. So for example, if I know I've found it, meaning it equals my key, then I'm done, right? Otherwise, I gotta check if I have to go left or right, or keep in mind that I could also run into a leaf node. So now we ask the same question. Is 13 less than 11 or is it greater than 11? Do we go left or right? Yeah, this time we're gonna go left, yes. Yeah, we're gonna go left. This is because 11 is less than 13. And now, look, 11 is 11, right? So that means we found this node and we can return it to the person that's requesting it. So in our algorithm, what we're gonna do, just because, like I said, last day, you can easily modify this algorithm, or at least the idea I've presented here at this stage, to make it so it actually returns you the data of the record if it's at an internal node. Because remember, if I hit a leaf node, as we're gonna see, that's possible too. So we can also modify this idea so that we could just simply return the node, and then we could do stuff with that node. We're gonna see that this algorithm is gonna be useful because we're gonna use it in other algorithms I'm gonna present you here today. Likewise, smallest, just like smallest, I returned a node, I'm gonna do the same thing here, but like I said, you can easily modify it to specifically return the value if you wanna be pure to the abstract data type. Is that clear, everybody? So I thought I'd go through this one more time with one more key. Let's try something else. Let's go, I have another example in the notes, but we're gonna try getting 4 this time. Let's try getting 4, just for the sake of ease. So, this time I'm not gonna trace through it, I'm gonna direct it with you, okay? So you gotta help guide me to where we need to go, okay? So, just to see if we get the idea. So, we're gonna start at the root. Okay, so we're gonna try to get 4. Do we go left or do we go right? Yeah, we're gonna go left, right? Okay, so now we're right here. We're at the 7 here. Okay, do we go left or do we go right? Left or right? Yeah, we're gonna go left again, exactly. Exactly, we're just gonna go left. Now we're at the 2. Do we go left or right? Left or right? Now we're gonna go right, right? Because 4 is greater than 2. Exactly, so then we're at the 3. Do we go left or right? Right, yeah. Good, you're doing a good job guiding me through here. We haven't made any slip-ups. And now we're right now at a leaf node. But notice the leaf node, we're at a leaf, which means that there are no more records for us to examine, and we can conclude we don't have it in our binary search tree, right? And this is actually the idea for how you can perform searches on a binary search tree. Now you can describe this idea in a couple of different ways. I'm gonna show you how you can describe it recursively. So I'm gonna give you a recursive algorithm for this get operation, but I want you to think about it. So I'll leave it more as an exercise for you to think about, as I think it's a rather important exercise. I'll let you just think about it. So I'm gonna describe a recursive algorithm for this. I'll encourage you to think about how you can translate this idea into an iterative one. So you're gonna find that it's gonna use a lot of similar elements to the algorithm that we've already seen for smallest. But now instead of it just being that we just go left, now we have to guide our exploration either left or right, just as we did. Okay. I'm hurrying. There we go. I swear I'm like navigating air traffic here. Just give me the reflective ones with the lights on them. Well, I'll guide them left and right. Okay. So let's write out the algorithm for get. Algorithm, we'll call it get. it's going to take in a node R, which will be initially the root of the binary search tree, and a key, the one that we're looking for. So the input will be some root R of a binary. Oh, that's right, BTS. I mean BST. BST. And we need a key K. And remember, this will return as a... It's going to return to us a node storing key K. Key K. Or, now this is the catch. Or it's going to return to us, because we can hit a leaf node, right? That's a possibility. So what I want us to have happen is if we fail to find it, remember, we're looking for the node that stores key K. I want it, if I say it fails, I'm going to hit a leaf node, right? I want it to return to me the leaf node where it would have been. This is actually going to be very helpful for the next algorithm we're going to see in a moment. Where K, so I thought the right, let's see, or a leaf that says or there, or a leaf where K should have been. Well, let's go over here. Should have been. So it's going to use a very similar structure. Remember, the binary search tree, you can think of it as a recursive structure. So just like trees, we talked about how naturally you can think of the binary search tree like I'm rooting it at some subtree. And this makes it very natural for me to describe to you what we're looking at. So that's why you're going to see me use this in our recursion here. So I'm going to start off with the same kind of case we had before, if R is a leaf. So if I'm at a leaf node, so imagine if R was the root. What does that mean? So imagine if R was the root of the tree, and it's a leaf. What does that mean? Well, it would normally mean if it was truly the root of the entire binary search tree, it would indeed mean the binary search tree is empty. But this is the thing. If you imagine I gave you a binary search tree, and imagine I passed along to you a node that was a leaf node, like we had in our example where we went all the way down to the bottom, and we hit a leaf node, well, you know right away that there is nothing else to examine. So it means that your search is going to fail, because if I'm considering the binary search tree rooted at that given node, that means that there's no more records to look at. So, wonderful. So that means that I'm just going to return this node. So remember, this is just the node where that record would be. So I'm just going to return that. Otherwise, we have to do our game of navigating down through the tree. Imagine it's Miss Kitty. I'm trying to guide Miss Kitty to the snacks, okay? So Miss Kitty needs like full like airline style guidance, just like a big airplane, to find the snacks. Sorry, I'm just losing it here. So I'm going to first start off by doing a check to see if the key matches. So the key stored in R is equal to K. If it's equal to K, then I could just simply return R, right? Because then I'm done. We found it. This should remind you of something, right? So I'll let you think about it, but we'll talk about it in a moment. Else if K is less than the key stored in R. So if it's less than the key stored in R, should I go left or right? So if K is less than the key that I'm currently examining, should I go left or right? Left or right? Left, yeah, exactly. So what I'm going to do is I'm just going to call recursively. So I'm going to return whatever the result of performing the get operation on the left child of R. So in that case, I will just call get again, but on the left child. Otherwise, we guarantee we're going to have to look right. Otherwise, return get on the right child of R, and that ends the else block. And that's it. That's the entire algorithm. Yes, 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 that's exactly what I was... So do you notice that there's actually an interesting idea being used here? It's being pointed out in the chat. There's a wonderful observation. Notice that this should remind you a lot of binary search, right? So do you see why we might call this a binary search tree? And there you go. That's why we call it a binary search tree. So see, now our ideas are all coalescing. So one common technique when you're trying to develop algorithms for data structures, you try to develop the data structure to take advantage of ideas that you know how to do efficiently. We know binary search is rather effective for searching, right? So why don't we adapt that idea to try to find things in the tree? And that's the idea of this algorithm. Now, there's some good news and bad news around that. I'll get to that later in this lecture. But does everybody understand the algorithm just before I get any further? Is it clear, everybody? Don't be shy. I'm really happy to answer anything. But you can imagine every time I asked you that question of left or right, it's akin to me saying, doing a recursive call. So the natural question is what the time complexity of the get operation is. So now naturally, you might ask, okay, so what's the worst case time complexity of this? So let's talk about that. So the worst case time complexity. Now you notice in the smallest operation, it didn't make much of a difference except for the fact that we're at the mercy of the structure of the binary search tree itself. However, what I would like to do in the worst case, just for our analysis, is we need to identify what will cause this algorithm to perform the most number of operations. Does anybody have any ideas what a good worst case scenario would be for our analysis? I'll give you a hint. It should remind you of something else. Yeah. When you don't have the key, there is no record with that key in the tree, which guarantees that we're going to have to explore this tree, but we're going to have to keep going until we hit what kind of node? An internal node or a leaf node? Yeah, a leaf node, exactly. We're going to hit a leaf node. So this is when k is not in the tree. So if you start off by ignoring all the recursion in this algorithm, notice that if I ignore all the recursion, I just count these all. Notice it's all just a whole bunch of constant number of operations, right? This is all just some C1 many operations, right? So if I ignore all the recursion, you can see that, right? Likewise, remember what we established earlier. We know that if I wanted to go exploring this tree, the number of calls, you know how I used that rather generous bound earlier where I added 1 onto it? We're going to use that bound exactly. So we start off with the initial call on get at that given, say at the root, and then what we do is we work our way down. Now, at what call does this thing just give up? Like, is it the recursive case, like all of this? Actually, sorry, this is also a base case, but I wrote it. Say if I have to do one of these calls, is it going to happen when one of these is happening, or is it going to be one of these two that happens? In fact, it's going to be the base case, but specifically it's going to be this one, right? It's going to cause this to happen. It's going to return R because R is in fact a leaf in the worst case. So we know that this is going to all the way get down to a leaf node, but the maximum number of calls that can possibly happen, so the number of calls is going to be at most the height plus 1, right? So that's the root plus all of the calls that happen for all of the descendants to get down to this leaf node. It's going to be no more than the height plus 1. So that's a period there. So the total number of operations in the worst case is just going to be C1 times the height plus 1. It's going to be at most this. But as we established earlier, which is big O of what? What is this? Big O of what? So what is it big O of? So we got C1 times height plus 1. It's big O of the height again. Exactly. So far we got a couple of operations that take big O of the height. I will tell you that this seems to be something that's going to come up over and over again if we keep adopting this idea. So at least it's one thing you can think about on the side. Like I said, I'm planting some seeds that we're going to talk about eventually. So next, naturally, we need to talk about insertion. So we talked about get, let's talk about put. And you're going to see that we're going to try to pick up some of these ideas and keep going. So I'm going to reuse this tree so I don't draw it again. So let me try to be smart about this. It's actually hilarious. One of my previous terms, what I did was I literally kept drawing this tree as a joke to the point where I think I drew it maybe 5 or 6 times in one lecture. So this year I'm going to be very conservative about how I draw this tree. So we're going to conserve the board space by making sure we don't waste this board over here. So let's talk about the put operation now. So I'm going to conserve our binary search tree. We're going to take care of it. Okay. So we have a method for finding records in a binary search tree, right? Remember our left-right process where we went left, right? Well, now we actually have a framework for how we can find things in a binary search tree, right? Let's just use that. So if I have something that works, don't reinvent the wheel, just do it again. So let's talk about put. So we're going to use get to find where the record with key K should go. And that let me fix that. Should go. And I'm going to say appropriately, because remember, the one thing we have to be careful about is that, remember, this is supposed to be for an ordered dictionary. We're not allowed to put duplicate keys in this dictionary. So now the cool part about this is that we know that our get operation will tell us if we're at an internal node or a leaf node, right? So here's the fun part about this, is that also gives us a mechanism to know if we run into a duplicate key or not. So I have a question for you. You know when we did this whole going left, then going right process, right? When I found a record, was it at a leaf node or an internal node? It was an internal node. Yeah, exactly. It was an internal node. So the question is, okay, so if I want a duplicate key checker, we have the ingredient, right? We know that if we get a duplicate key, it has to be when get gives us an internal node. If it's a leaf node, then we have a brand new spot where we can put it in without a duplicate. Does everybody get it? So if I'm doing this get operation at first and I've run into an internal node, that means I found it already. So to detect a duplicate key, get gives us an internal node. So you might naturally say, okay, so what does that mean for us? Well, I'm going to talk about this in terms of Miss Kitty. You know how I was guiding Miss Kitty down? Well, I didn't tell you exactly where Miss Kitty's snacks were. Miss Kitty's snacks were going to be in a cute bed where we need to make sure there's enough security there for the cat to lay in the bed. So we want to make sure it's nice and cushy, not a really rough surface for the cat, because Miss Kitty just likes to be pampered like that. So what we're going to do is when we do our insertion, we're going to make sure that we still maintain the structure of a binary search tree. But remember, so based as a consequence of this, are we going to do our insertions at internal nodes or at leaf nodes? So which one? So we know that if we get an internal node, we got a duplicate. So what does that mean? Yeah, so it means that we're going to work our way down the tree just like we did before, where we're going to play this game of left or right. And when we find a leaf node, we're going to put our data inside of this leaf node. Then we're going to create 2 leaf nodes for this node to give it security to ensure it's still a binary search tree, right? Because remember, a binary search tree in our definition, it says that every record is in an internal node. So we need to make that node an internal node, just like I gave Miss Kitty a nice cozy bed to sit in. They eat all of her snacks. So let's do an example of what I mean by this. So we're going to try putting in 12. So let's try putting in 12. So imagine I give you the root here, and I give you 12. So, and keep in mind that typically the way it works is that you're given some record. So I'm just going to presume that there's more stuff. Say there's a part of your record. Say 12, and then there's some data. So we play the left-right game, remember? We go, in this case, do I go left or right? I'm going to put 12 in. Some record with 12. Do we go left or right? Left or right? Remember, we're going to start using, yeah, there we go. We're going to go right. Because remember, the whole idea is we're going to use get to find where it should go. And then we're going to do the insertion right there. Next, left or right? Left or right? We're at 13. We're going to go left because remember, 13 is less than 12. Sorry, no, 12 is less than 13. That's a Monday moment right there. Then we have 11. Now, 11 is less than 12. So which direction should I go, left or right? Yeah, this time I should go right because 11 is less than 12. I'm getting the inequality in the right direction. Again, fun day moments, I guess. Fun day moments. So now I know I'm going to go right here. So that's the node that I would put 12, right? Just like in our get algorithm, it gives us this node. So it means what I'm going to do is I'm going to insert the data into this leaf node. So I'm not going to delete the leaf node. Instead, I'm going to use this data attribute to insert the data in for that record. So I'm just going to insert that in. So I put 12 in right here. And then I'm going to create 2 leaf nodes as its children. So this is so this is all actually our put operation does. It uses get to piggyback to get to where we need to put it. Then we do the insertion by putting the data into this node's data attribute. Then we create 2 leaf nodes as its left and right children respectively. So this is actually the same reason why when we started off with an empty binary search tree, as I mentioned in the last lecture, where you start off with an empty one like this, just like you imagine Miss Kitty finding an appropriate spot, what happens is the data gets gets inserted into this node, so you end up with a node that looks like this, and then you create 2 new children, and this is actually how the binary search tree grows. So you just look at it like Miss Kitty finding a bed, and we put down the legs of the bed to make sure that Miss Kitty has a nice soft landing. So are there any questions about our idea? So does this seem okay with everybody? Like, does this idea make sense with everybody? So this is also one common thing that I would like you to think about. If you have something that can achieve something, rather than reinventing it again, just use those ideas. Like I said earlier. So same idea here. I'm going to use get to help me do the insertion. It's going to do all the heavy lifting. So that brings me to the algorithm for put, and you're going to find it surprisingly simple because we're going to use get. So let's go over there and let's see what this algorithm looks like. So I'm going to try reusing some bits of this just to illustrate a point, but a little bit, it's a bit different. It uses get, but we're going to keep it rather simple here. I'm coming, camera. The camera is just, I am moving a bit slower today. Okay, so we're gonna use some bits of this. Most of it I erased though. I'm trying to reuse things on my end here. So we're gonna have algorithm, it's gonna be put, it's gonna take in a root, it's gonna take in a key, and it's gonna take in the data or value for the record. So remember the record is a pair, we have a key, and you have some value or data that's associated with it. So I'm going to have the root of the BST, a key, and the data associated with that record with key K. So to make this easier for us, what I'm going to do is I'm going to make it actually return a Boolean value. It's going to return true if the insertion was successful, or false if it failed to do the insertion. So we're going to use, so the way you would see this pop up, for example, in your assignment, is that this will actually give you the information to know whether you should throw an exception or not. In the assignment, it's the duplicate key exception. So the output here is true if the insertion was successful, if KD was added to the BST. So it's true if KD was added to the BST. False otherwise, meaning that the insertion failed. So you're going to see this is going to be really short because we're going to piggyback off of get. So if, sorry, actually no, let's not do, we don't actually even need to check if it's a leaf even. Watch this, watch this. I'm going to reuse get. So I'm going to have a node I'm going to label P. Get, and I'm going to use R and K to get the node where it would be, and this will be what P is. And then all I have to do is ask if P is an internal node, right? So if P is, I'll say P is internal. If P is internal, which means it's the opposite of being the leaf. So if it's not a leaf, it has to be an internal node. So if you're ever given a function that say, oh, I want to know if it's an internal node, you can always just make it not is a leaf, and that gives you if it's an internal node. Very often when people implement these things, usually they pick one or the other, then they just logically negate the other one's result. It's a pretty easy way to implement is a leaf or is internal. So if this is the case, then you know, as we established, that the insertion is going to fail because we hit an internal node. It means there's a duplicate key that's going to come in. And that means that we don't want to put it in. We're not going to put it in. So now, otherwise, I'm hitting a leaf node. I'm at a leaf node. So as I'm going through this process I had over here, I'll be at node P. So I'm going to update its key and its data. Because remember, right now, this information, it might actually just simply be a pointer to some object. Right now, that's currently null pointer. For the sake of simplicity, I'm going to just write them out separately, but typically if you have all of your records and your key data tied to the record as just a single object, it'll just be that you update it with the record. So it would just be like, okay, here's the object in question. I'm going to update the data attribute of the node. So I'm just going to write this just explicitly, though, with keys and data like this. But the point is that this is where you would update the data attribute of your node, where I'm just updating the key and the data of the given record. So then you lastly create 2 leaves. So 2 leaf nodes, and set them as children of P. And then you just return true. And that's it. That's it. So remember, the whole process is I just use get, define where it needs to go. If I hit a leaf node, I'm just going to put the data for my record into that node, and then I create 2 leaf children. Now I have a question for you. So when you read something like this where it says create 2 leaves and set them as the children of P, when you read this, is it only just that you have to update the left child and right child of P? Or is there another step I have to do? Like when you think about this, because remember, it's setting them as the children of P. So remember, imagine you have P and you just assigned its data, like here's the new record. I'm gonna, actually, well, technically speaking, it'll probably be a pointer. So it'll be a pointer to some key data pair like this, probably. And I create these two children like this. Well, I would need to update the left attribute to point at one of them, the right attribute to point at these. But what about the leaf children? Do these have to have any information updated for them? Yes, the parent attribute. I bring this up because it's a very easy thing to miss or forget. Is that, remember, each one of these nodes, it has a left, remember it has the left attribute, a right attribute, it has data, and it has a parent. So remember, the children need their parent attribute updated. So you just make sure that they're pointing back at P and you're all good. So this is a very basic step that's very easy to miss, especially when we're implementing things in C++. Some languages it's a little bit more convenient, but this is a step that's implicit in this step. Is that clear, everybody? I mention this because it's a very common thing to miss when implementing this operation. Okay, so this brings us to the time complexity. So, well, this is the great part. Now that we have actually other things going on here, we know that get here, this operation takes big O of the height, right? This get operation performs, it's big O of the height. All of these other operations, how many operations are these in total? Like all of this. In terms of big O, what would you say this is? It's constant, exactly. So all of this is just big O of 1 many operations right here. So if you add these number of operations together, you can say that the time complexity in the worst case is going to be big O of the height again. Do you see how when we start piggybacking like this, the analysis suddenly starts becoming a little easier to play around with? It's not going to be the case always when we have this. So it brings me to our next operation, which I would argue is probably the most complex of the set I'm going to show you here today. It is the remove operation. Now, very often when students first learn this data structure, sometimes some profs will deliberately ignore this operation because some think it's a little bit too easy or too hard. Some say it's a little too hard. I think it's not that bad, really at all. As long as you understand the 2 things that make it work. So let's talk about the remove operation. And you'll see that it's going to just use properties we know about binary search trees. So far I'm doing okay, right? So far I haven't drawn this tree again yet. So we're going to try to figure out how we can remove the data or remove records from a binary search tree. So one big question we have is, so we know how to find things. We know how to insert new data into the tree. The real question now is, how do we remove data from the tree? So now this is where things are going to get, and I don't mean to intimidate you or anything with this. It's actually, the only thing I'm mentioning here is that there's going to be some steps that are going to be implicit in the way I describe it to you. That's the only thing. The ideas, you'll see where we're going to derive them from. So watch this. So I'm going to ask you a very basic question. If I were to try to delete this node here with the record 3, if I were to just say take this and replace it with a leaf node, would we be okay? Would it still be a binary search tree? So far I'm getting yeses and okays. Yes, yeah. So notice if I were to just replace 3, like I took all of this, just imagine it's a leaf node here. In fact, if I were to just imagine I just took this and I pretended that this right child here, that is a leaf node, was just the node that was right here, you could see that that wouldn't change anything about things other than getting rid of this record with key 3 in it, right? So far we have something to do with removals, but it doesn't seem to work always, right? So notice that if I try just doing that, that's easy enough, right? It doesn't destroy anything about the binary search tree. It removes the appropriate node. But can we do the same thing, for example, at node 10? Like, can I just do the same thing here? Can I just like pretend this like that doesn't exist, and then I could just like, okay, well now I have this, and it's just gonna be gone. Now we have just 2 binary search trees or something. Now technically speaking, like if I just dissect and get rid of this right here, these would technically be 2 binary search trees. That's a little exercise I'll let you think about. But this doesn't seem workable if I want to keep it as one single binary search tree. I can't just like destroy one of these and, I don't know, like set up on the altar of the binary search tree gods or something. That doesn't work. It just doesn't work. But I want us to think a little bit carefully about what it makes a removal easy versus one that requires us to think a little more carefully about these cases. So notice here that when I have it, like for example, is 2 relatively easy for me to delete? Like if I want to get rid of 2. Well, think about it. If I have 2 here, notice that one of them is a leaf node, right? You could do pretty much the same idea I just described a moment ago. If you cover those up, notice that the other node is an internal node, and it could just, imagine you could just slide this up into its place. Do you see that there's something rather interesting going on here that allows me to have very easy removals versus these ones where that isn't possible? Is there some characteristic that pops out to you? So like what property like allows me to just simply just get rid of these 2 nodes right here, and I could just simply make this, for example, the left child of 7. So what stops me from doing this with, say, any one of these nodes like node 10? I'll ask this in an opposite way if it makes it easier. Why can't I apply that trick on node 10? So why can't I do it there? So think about it in terms of what we did. So remember, notice that I could always just get rid of one child and that node if I have a leaf node as one of my children. So yeah, look, it seems like, yeah, no, notice that there's, if I look and examine the node I want to delete, notice here that there seems to be this nice property. Notice that I couldn't do it with 10 because both of its children are internal nodes, right? Both of them. But if you flip this logic on its head, so you negate that reasoning, what that means is actually that if you wanted to say, oh, what we've been calling this easier way of removing, or what seems to be easier for us, it seems to be that there's at least one leaf node for its children. So notice that if I have at least one leaf node, I can apply this trick I was doing down here with 2 and 3. Likewise, I can do the same thing with 11. Like notice I have a leaf node here. I can just get rid of that. And now this could be the left, say 13's left child could be 12. But yeah, so exactly everybody. So it looks like we have two cases. There's only two possible cases then, right? So it seems like there's this case where I can just cover these two up and slide that into where it would have been, or have it where I have two internal nodes as children. So these are going to be the two exact cases that come up in our algorithm. So the one with at least one child is the easy, well, I wouldn't call it the easy case because it's trickier to implement, but it is the one where we're able to just cover things up like this. The other one will be when we have two internal nodes. So I'll call these case 1 and case 2 respectively. So there are two cases. So the first one is, so if I'm at a node that I want to delete, so I'm going to suppose, so P is to be deleted. So if that's the case, if P has at least one leaf child, so it has at least one leaf child. The other possibility, and this is the only other possibility that could happen, is it has both of its children are internal nodes. If P's both children are internal. So there's two possibilities. So we see that we could do these easy removals in case 1. Case 2, it seems like we have to do a bit more work. So that brings me to one interesting observation about binary search trees. So at first, number 2 looks a little bit daunting, doesn't it? We know how to do 1 roughly. We'll see the algorithm shortly, but we get the idea, right, everybody? That you just simply can delete that node along with the leaf node. You can substitute in its place the node that is the other child, because you can guarantee it's either a leaf node or an internal node in its place. But remember, all of this is just pointer adjustments. So the idea of me putting it in its place is just pointer adjustment. So if this is, say, for example, the left child of 7, I would make 3 the left child of 7 instead, if I were to get rid of 2. Sometimes we might have to update the root of the tree, but I'll get to that in a moment. Let's look at case number 2 here. Okay, I want to propose an idea to you, and we'll walk ourselves through it to derive the idea, or at least one idea for removals. So suppose I was wanting to get rid of 10. Now, remember, we need to maintain that this is a binary search tree. So at the beginning of this, before I get my hands on it and get rid of some nodes, it was a binary search tree. Now I want it to stay a binary search tree when I'm done. So this is an example of an invariant. So the idea is that before, after, they have the same property, that it's a binary search tree. So we use this idea very often in algorithms and data structures. We've used this idea before, but we're going to see that this idea is very helpful when we think about the present state of the data structure. So I want you to think about this. Okay. Well, if I were to list these out in order traversal, I would have 2, 3, 7, 10, 11, 12, 13, 16, right? It would come out in sorted order. What's the successor of 10? So what comes after 10? 11. So I have an interesting question for you. Suppose we look at 11 over here. Notice that if you look at this right subtree right here, if you look at this one, there's a very interesting property we have. If you go and look at 11, is it the smallest key? Is 11 the smallest key in that entire subtree? It is. It is, because it's the successor of 10, which it means that by definition, it is the smallest key that is larger than 10. But that is also guaranteed to be, so does anyone have any ideas of how I can find 11? Any ideas at all? What algorithm do we have for that? Smallest. So I got one suggestion about smallest. Yeah, smallest seems like a very natural one to use to get 11, like that node there. But there's another neat property in display. If I go far left as possible, and I hit the leftmost internal node, what can I guarantee? What can I guarantee about its children? What about its children can I guarantee? So remember, we're looking at the smallest key in that right subtree. So does it have two internal nodes as children? Yes or no? Well, think about it. If I go far left as possible in this tree here, notice that there is a leaf node right here. It's guaranteed to exist. But if I were to say, for example, take this data here, copy it up over here, and then delete this node, what case would I apply to this node if I wanted to delete this one? Suppose this was P. Which case of these two would I use? The first case, yes, case number one. Does everybody see what we're going to do now? So whenever I'm going to do this, I'm going to find the immediate successor of whatever node I'm at, which is just simply getting the right node's the node with the smallest key of the right subtree. So I'm getting very excited about this. But yeah, so notice that if I find this one here, I can copy, and keep in mind, you need to do a deep copy of this data. So you're going to copy this data into your node, and then you can just simply delete this node and get rid of it. And we know how to do that, right? So that brings me to the removal algorithm. So let me show you this removal algorithm. So we have these two cases, and that's how the pseudocode is going to be laid out to you. So I'm going to walk you through this. So let's do the remove algorithm. And while it looks like we only have a couple of cases or something, it's actually conceptually not that complicated. The only thing I warn you about is that looks like there's some pointer adjustments you have to do here. So you have to be very careful about this process. So I'm going to give you some tips when it comes to this. Okay, so let's write out the remove algorithm. So we got the algorithm remove. So we're going to remove, and I'm going to write this in a manner that I'm given the root R. So this would be some root of some binary search tree, and the key of the record I would like to remove. So input will be a root R of a binary search tree and key K. You got to remember, when I talk about this root R, it can be, technically speaking, the root of some subtree. So when I talk about the subtree being rooted at some node, R can be that. So keep in mind, there's, like I said earlier on in a previous lecture, there's like the root attribute of the binary search tree itself. And then there's this idea that I can recursively call on this, for example, with some node. And conceptually speaking, that would be what we would call the root of that subtree. So we've used this idea before when we were doing the get operation, for example, which you're going to see very quickly we're going to take advantage of again. So we're going to see how much of this I can write here. So it's going to be, again, a Boolean function. So it's true if node with key K was removed, false otherwise. We'll see if we run out of space here. I might have to start writing it over there. We'll see. We might get lucky. So one thing I want to stress is you can easily modify this algorithm. So if it does give you the false case, you could just simply throw an exception. So first, you start off with the same way we did our insertion. So we're first going to apply the get operation to find the node for which we're going to perform the removal. just like we did our insertion, same idea. Now I'm going to check if P is a leaf. So if P is a leaf, does that mean we successfully found a record, or did we fail to find a record? Did we succeed or fail? So if we hit a leaf node, we're going to fail, right? That means that we didn't find it. So I'm going to make sure it returns false here. Now, otherwise, we can now proceed with the actual removal algorithm. So now we're going to talk about our ideas we just had. So now I'm going to check for case 1. If P has a child, C, that is a leaf. That is a leaf. Then, so this is going to be case 1. So I'm going to check if P has a child that is a leaf. So one thing you'll notice very quickly is that this step right here does not sound like something you can check in a single line, or at least very trivially in one line. So when you're actually implementing this, you need to figure out if this child exists. I recommend you keep a pointer to it and determine if it's on the left or the right or something like that. It's often helpful to know which child is this given one versus another one, which I'll explain in a moment. So what are we going to do? We're going to actually keep track of a couple of nodes here. Actually, technically, it's a few. So I'm going to have P prime be the parent of P. And also going to have another node I'm going to call the other child of P. So it's going to be its sibling. So they're going to be 3 nodes. So suppose that I am at some node here. So this is the one I want to get rid of. And this is its parent, if it exists. And then I'm going to have 2 other nodes. So one of them is going to be guaranteed to be a leaf node. I'll call that C. The other child may be a leaf, or it could be an internal node. But I'm going to call it C prime. We don't really care the difference between C prime being an internal node or a leaf node. It's just some node. The implementation of this, it won't make any difference. This is just one edge case where this representation makes it a little easier to play around with. So we have these nodes. Now remember what I told you. The goal here is to get rid of P and a leaf node so that I can replace it with everything else. So watch this. So I'm just going to put that over here. And that's what I want, right? That's what I want. And that's what the algorithm's going to do. So we check if P is the root. So I'm going to first check if P is the root, I'm talking like the root attribute of your binary search tree. Then, if this is the case, then what you're going to do is you're going to make C prime the new root. So for example, if I don't have this, this is the root right here. So all I'm going to do is just get rid of this, and now this is the root of the binary search tree. So remember, you have to update these pointer adjustments to make it so that the left, right, and the parent are updated. So you have to be very careful when you're doing this. I recommend you doodle it out step by step. Otherwise, you're going to make C prime the child of P prime. Now, note that you will have to figure out which one. Is it the left child or the right child? So when you do this step, you're going to have to determine if P was on the left or on the right of P prime. Okay? So this is case 1. So this is the end of case 1. And after this step, then you can delete anything you need. So in this case, notice that C can go, so you can get rid of C. You can also get rid of P, right? After this is done. Because remember, at this stage, it looks like this. So is that clear, everybody? So that's case one. So this is the one where we said that removals are pretty easy. I will tell you that usually this is the one that you have to be careful when you're implementing it. But as soon as you get it right, it's so worth it. So I'm going to write out the second case. I'm going to do it over here just because we ran out of space over there and I don't want to squish it over there. It's really short. You're going to see, ironically, the second case is more complex than the first case, but not very much, not. So, like I told you, if we have an idea that works for what we need to do, let's reuse it. So, here's case two. So we're not done the pseudocode yet. We got our else block that comes after this. So this is case two. So what we're going to do is we're going to get a node that we're going to call S. So this is smallest. So I'm going to call smallest on the right child of P, right? That's what we established earlier. So we're going to go right, and then we can compute the smallest on that. Remember, this is the node that we want to copy the data from, and then we're going to get rid of it. Because we know that we can use case one. So we're going to use compute smallest on the right child of P. And then, of course, we need to copy the key data or record information from S to P. Now, I must really stress this. You need to deep copy. I mean, you're going to straight up copy the attributes themselves. If you just copy the pointer over, remember in case one, if say something comes along and deletes something, say if you're using literally just the pointer and you delete and you go delete on the node and you follow that pointer so you get the data at that node. If you delete that, what happens is you might actually be deleting the data in actually two nodes. The one you actually want to delete, which now is S, and also the one you copied the data to at the same time. This is why when I say this step, just put beside it, say deep copy. Please just remember to do a deep copy. It's very easy to forget that. Believe me, when you're debugging, when you run into this, what very often happens is you'll notice that if you try doing a two-string, where you print it out, you'll start seeing strange things happen to the string representation. You're like, I didn't delete that. Why is that in there too? It very often it's because of a simple little error like this, where you don't make a deep copy. So then all you do is you just call recursively on S, but you're going to use the key in S. Oh yeah, I also have to return true after the else block. So after the else block, I'm going to return true. And that's the end. That's the end of the remove algorithm. So here's one neat thing I want to point out that's going to make the time complexity go a lot faster to do. Well, remember, this is technically speaking a recursive algorithm because it recursively calls it on S right here. But notice that when we do this case right here, it looks very specific, right? Remember, I use in the remove algorithm, I apply get, and then I find that given node, and then I perform, in this case, case one. So it will be guaranteed it's going to look something like this, where you have C, and then you have C prime, then there's P. There may be a P prime up here. But the point is you're exactly at that spot already. So when you try to determine the time complexity of this only happens once. It only happens once. So you could just say case one happens. So it's not going to do any more calls than this. So that's one big observation I want you to have here. So once you notice this, this algorithm is actually surprisingly simple to analyze because it just uses get, right? It uses get, and we know what's the big O for get? It's big O of the height, right? So it's big O of the height. Then you have your cases where you check if it's a leaf, and you do a whole bunch of pointer adjustments, right? There's nothing else happening other than that. And then there's this one call, but this happens at most once. So even if I threw in big O of the height for this, it wouldn't make any difference. So if you want more details about this, I'll have a little bit more details in the notes, but you can see that we're piggybacking off of get and the fact that this only gets called once in the entire execution of the remove operation. So all of our operations that I've shown you up to this point all take big O of the height. There's one other operation I did not show you here that I want you to take a look at. It's called the successor. So we talked about the successor. See if you want to compute the successor more generally. So if I gave you, so remember, when I do the removal, the successor is a very specialized structure here because I have two internal nodes as my children. I want you to take a look at the successor algorithm in the notes. It'll be right there in the notes immediately after this on page 115. One other thing I wanted to point out to you is that the structure of the binary search tree, we're at the mercy of it because all of our operations that I've shown you, including this one, all of them take big O of the height. So remove, get, put, they all take big O of the height. We're going to talk next time about how bad that can get. And it'll motivate our next topic, which is AVL trees. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.